Hello everyone, this is lecture 15, number bases. In this lecture, we're going to talk about different bases in the number system, including base 10, and I'm going to show you some example related to converting numbers from one base to decimals. So number bases represent the number of unique digits in the system. So number bases represent of unique digits in the system. For example, you have the system of numbers that we are using in day-to-day life situations, that is base 10, because it has 10 unique digits from 0 to 9. So for base 10, this has 10 unique digits from 0 to 9. We can talk about base 5, and in base 5 it has 5 unique digits of 0, 1, 2, 3, and 4. We're talking about binary system. The number of digits are going to be 0 and 1, and this obviously used a lot in computer science. You can have octal system, which is base 8. And in this page, you have 8 unit digits of 0, 1, 2, 3, 4, 5, 6, and 7. And we're going to look at hexadecimal system, which is base 16. And for hexadecimal, the digits it's going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And for this system, after 9, we're going to go with the letter A, B, C, D, E, and F. And altogether, they go in from 0 to F, and there's going to be 16 unique digits. And in addition, when you do operations on this type of hexadecimal system, what we're going to use for A is equivalent to 10, B is 11, C is 12, D is 13, E is 14, and F is 15. So you have to keep in the back of your mind that A is equivalent to 10, B is equivalent to 11, so on and so forth. And how could you represent a number in decimal system, which is base 10? And from knowing how to represent the number in decimal system, we're going to move on to converting the number from one system to another system, or the number from one base to another base. In the next example, I would like to show the representations of a number in decimal system. So show representations of each number in decimal system, which is base 10. Now for integer, let's consider the following number of 5,362. So to stay consistent with this particular lecture, I'm going to indicate that this number is in base 10, or is in decimal system. So this number can be expanded as follows. So this is 5,000 plus 300 plus 60 plus 2. And if you use a calculator, you add all of these numbers together, we're going to get back at 5,362. Now we further expand this one. 5,000 can be written as 5 times 1,000 plus 3 times 100 plus 6 times 10 plus 2. And we're going to represent 1,000 in terms of base 10. That means 1,000 can be written as 10 to the third power, or 10 to the power 3. 100 can be written as 10 to the second power, or 10 square. And of course, 10 is written as 10 to the first power. Now we go into 2. Even though 2 stands by itself, it can be written as 2 times 10 to the power 0. So 10 to the power 0 is 1. So this is 5 times 10 to the third power plus 3 times 10 square plus 6 times 10 to the first power plus 2 times 10 to the 0. So we just expand this number of 5,362 in base 10 in terms of 5 times 10 to the third power plus 3 times 10 to the second plus 6 times 10 to the first plus 2 times 10 to 0. Now that is for the integers. What about fractions? So for fractions, Let's consider the following example, 0.526, and this is still in base 10. This can be written as 0.5 plus 0.02 plus 0.006. And again, when you add all of these numbers together, you want to get back 0.526. And this number can be represented in terms of base 10 as follows. So 0.5 can be written as 5 times 10 to the negative 1, plus the next number, which is 2 times 10 to the negative 2, plus 6 times 10 to the negative 3. So we again show that this number can be written as some combinations of base 10. So in general, the representations of the number in the decimal system is going to be d sub n minus 1, for d is the digit. This is the n digits, this is the n minus 1 digit. Going all the way down to this is d2, d1, d0. So this is the 0 digits, which is going to be the ones, the tens, the hundreds, the thousands, the 10,000s, so on and so forth. So all of this is just integers. Now you're going to incorporate fractions as well in the representation. So you have the dot here, and after the dot, you're going to have the digits written as d negative 1, d negative 2, so on and so forth, down to d negative n. And this is in base 10. So this digit is going to be tens, hundreds, thousandths, 10,000, so on and so forth. And in terms of the representation with base 10, what you're going to do is this. So d, n, the digits at the nth position, multiply with 10 raised to the n power, plus d sub n minus 1 times 10 to the n minus 1, so on and so forth. Go to the hundreds. So you have d2 times 10 to the second power, plus d1 times 10 to the first power, plus d0 times 10 to the 0. So all of those represent integers. Now after the dot, or after the decimal point, then you have the fractions. So you have d negative 1 times 10 to negative 1, plus d negative 2 times 10 to negative 2, so on and so forth, to d sub negative n times 10 to negative n. So we're going to take this form and going to show the representation of the following number. So here I would like to give another example, that it can you represent the following number in terms of base 10. So 543.67 in base 10, and you're going to get, so you're going to see that is the ones, the tens, the hundred. So you take 5 times tens to the second power, then 4 times 10 to the first, plus 3 times 10 to the 0. And then after the point, you're going to take 6 times 10 to the negative 1, plus 7 times 10 to the negative 2. And that's how you represent a number in the decimal system. Now you can do the same thing for all the bases as well. You can do this for binary system, you can do this for octal system, you can do this for hexadecimal system as well. The change or the difference is going to be is that it's no longer base 10, of course. It's going to be base 2 for binary, it's going to be base 8 for octal system, and going to be base 16 for hexadecimal system. So you replace the number 10 for 2 in the case of binary, replace 10 with 8 in the octal system, and replace 10 with 16 in the hexadecimal system. So let me quickly do this for binary system. So binary system. So a number in binary can be expressed as, so you have the digits as the positions n, then the n negative 1, all the way down to d2, d1, d0, and then you have the dot, indicate we are going down to fractions. So you have d negative 1, d negative 2, all the way to d negative n. This is base 2, and this can be written as d sub n times 2 to the power n, plus d sub n minus 1 times 2 to the power n minus 1, plus dot dot dot, plus d2 times 2 square, plus d1 times 2 to the first power, plus d0 times 2 to the 0. And then for fractions, you do d negative 1 times 2 to the negative 1, plus d negative 2 times 2 to the negative 2 plus all the way to d negative n times 2 to the power negative n.
And that is how you write a binary number in decimal system.
And by using these representations, you could be able to convert the number from one base to decimal system. So, example. Now I have the number 110101 in base 2, or in binary system, and we're going to convert this number into a decimal system. Okay, we're going to start out with the first number from the left. So how many number that we have here? So 0, 1, 2, 3, 4, 5. So the first one is 1 times 2 to the 5th power. The next one is 1 times 2 to the 4th plus 0 times 2 to the 3rd power plus 1 times 2 to the 2nd plus 0 times 2 to the 1st, and then 1 times 2 to the 0. And for 1 times 2 to the 5th power, you have 32 plus 16 plus 0, because this is 0 times 8, plus 4 plus 0 again, then plus 1. And if you use a calculator, this comes down to be 53, and this is in base 10. And this number right here in binary system is equivalent to 53 in base 10. Now in terms of number with fractions, how could you do that? So 101.11 in base 2. Now you have 0, 1, 2. So 1 times 2 square plus 0 times 2 to the 1st power plus 1 times 2 to the 0 plus 1 times 2 to the negative 1 plus 1 times 2 to the negative 2. So for the first calculations you get is 4 plus 0 plus 1. Then 4, 1 times 2 to the negative 1 is going to be 1/2 of 0.5. And here, for 1 times 2 to the negative 2 is going to be 1/4, or 0.25. And if you add all of the numbers together, you're going to get 5.75. This is in base 10. Not only for binary system, again for other bases, you can use the same approach to get to base 10. Okay, now let me convert one number in base A to base 10 and one number from base 16 to base 10 as well. So I want to convert the number 127.4 in base A to base 10. What I'm going to do is, you see that's very similar setup to what we have seen so far. So this is 0, 1, 2. So the digit 1 multiplied with 8 raised to the 2nd power. Why 8 here? Because we are working with base 8. Then the next digit is 2 times 8 to the 1st power plus 7 times 8 to the 0. For fractions, you have 4 times 8 to the negative 1. Now for the first number is going to be 64. The second calculations give me 16, then 7 plus 0.5. So 4 times 8 to the negative 1 is 4/8, or 1/2, or 0.5 for that matter. Add everything together, we're going to get 87.5. This is in base 10. Next example is that I want to convert the number B65F in base 16 to base 10. And again, this is in terms of hexadecimal system. That means in hexadecimal, the number of digits is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. For A is equivalent to 10, B equivalent to 11, C equivalent to 12, D equivalent to 13, E equivalent to 14, and F is equivalent to 15. So for this number B65F, base 16, you're going to do, again, the number of digits is going to be 0, 1, 2, 3. So B, which is equivalent to 11, times 16 to the 3rd power, plus 6 times 16 to the 2nd, plus 5 times 16 to the 1st, plus F, which is equivalent to 15, times 16 to the 0. Then we're going to use a calculator in this case, and we're going to get the first calculations give me 45,056 plus 1,536 plus 80 plus 15. Altogether, we're going to get 46,687. This is in base 10. So that's it for this video. In the next video, we're going to learn how to convert an integer from decimal system to another base.